So the last two lectures went through the expectation maximization algorithm, or EM algorithm, from a high level perspective, first in terms of schematics and second in terms of sort of more mathematical description of what the algorithm involved. Now we're going to go and implement it, talk about implementing it for a very simple example. And of course, that's going to be our running example of mixture of Gaussian models, which are used for clustering. Now, in order to save on algebra, and make sure that I communicate the main conceptual messages, I'm going to make things slightly simpler than the full general case. And the way we're going to do that is we're going to assume that we have got just one-dimensional observed data x. So the xn's are going to be scalar varied valued quantities. And so our mixture of Gaussians model, we could actually plot an example of it, might look, you know, something like this. Okay. So this we're going to do to avoid having to have things like covariance matrices flying around, and of course all of the extra algebra we need for dealing with to deal with vector valued x's. In general, everything just goes through in exactly the same way. In those cases, it isn't really conceptually any more difficult, just more bookkeeping is involved. So we're going to keep things simple for those reasons. Okay, so in that case, where we have scalar observed variables x, our parameters correspond to the following. We have k, big K means. So k, remember, is the number of clusters. We have big K variances. So our means are just going to set the mean value for each one of our components. And our variances, of course, just set the width of each one of these K components here. This might be an example with big K equals to 4, for example. And then we also have big K mixing proportions as well. So K numbers that sum to 1, and each of them are not bigger than 1 individually, and they're non-negative. And then, of course, we have one latent variable per data point in the clustering case. Note, the EM algorithm can handle multiple latent variables for data point. There was nothing special in the way we wrote it down that required us to have exactly one latent variable per data point, but that is true in the clustering case. In the clustering case, you have a single latent variable, S, which takes values 1 to K, indicating which cluster you come from. So that's what our latent variable is going to be. Good. And first of all, what we're going to consider is writing down the E step for this algorithm, for this model, I should say. And in the current case, of course, these are the equations which are given by our mixture of Gaussians model. The probability of coming from cluster K a priori is equal to pi k, and the probability of seeing observed scalar value xn, given that you came from cluster K, is equal to a Gaussian with a mean associated with that cluster. That's these mu k's in here, and variance sigma k squared. Good. Now, so remember the definition of the E step. The definition of the E step was simply that you should update all of your Q distributions here to be equal to the true posterior distribution over S, over the latent variable, which you don't observe, given the observed data in here, okay? Given the observed data xn. And of course, for this purposes, in the E step, the parameters are fixed. Okay, so we're viewing the parameters as fixed. They're fixed to the current value given to us by the previous M step or by the initialization. Good. Okay, so the way that we can compute this is just by using Bayes' rule. Okay, so this thing, P of Sn equals to K, given xn and theta, that's equal to, we know from Bayes' rule, is equal to the prior. Well, let's just write it out as the joint to start with. Do this in 2 steps. Given theta divided by P of xn given theta, and this thing is equal to P Sn equals to K given theta times P xn given Sn equals to K and theta divided by, divided by P xn given theta. Okay, this is just simply applying Bayes' rule in this case. And we know these quantities. So we know what this thing is. This thing is just our Gaussian, which I've written up actually below here. This Gaussian in xn with a mean mu k and a variance sigma k squared. It's just this expression here. Sorry, I've drawn the arrow to the wrong place. Almost deliberate mistake. This thing, sorry, is our Gaussian. And the term out front here, this thing, which I was incorrectly attributing to the Gaussian, this thing is just our pi k. And again, I'm going to forget about the normalizing constant here. So I'm just going to deal with things up to a constant of proportionality, and we'll deal with the normalizing constant in the next line, actually. So what this line says here, it says that the probability of coming from cluster K is proportional to this term UNK, and the UNKs are just the Gaussian evaluated for that value of xn and that cluster K, multiplied by the prior probability of coming from that Gaussian, which is just the pi k. And then in order to get back the constant of proportionality here, the p of x given theta, we know that p of xn given theta is just equal to sum on k. This is the sum rule here. P Sn equal to k, comma, xn given theta, which is just the sum over k of UNK. And so the normalizing constant here is what we're going to call QUN. We're using these placeholder notations of UNK and UN because these are the actual things we're going to have to implement on a computer. So this thing is equal to P xn given theta. Good, and then that means we can write down the full update in this way, like this. So practically, on a computer, what you would do, let's just sort of fill this in a sort of very explicit way. You would implement this line. So for each data point and each cluster K, you multiply the prior probability pi k by the Gaussian, which depends on the actual observation here, of course. That gives you the unnormalized posterior probabilities UNK. You compute the normalizing constant by summing over K. So this would be a matrix, and then this would just be a vector. And then you renormalize in order to get the actual probabilities. And for historical reasons, those things have often been denoted RNK, and they're called responsibilities. You can intuitively think of these as how responsible each cluster is for each data point. So for each of the big N data points, we have big K numbers, and those big K numbers intuitively are how responsible each cluster was for generating that particular data point. These are, of course, from a probabilistic perspective, categorical distributions, the categorical distributions just come from the prior and the likelihood renormalized, which is what we've been stressing up here. Good. Okay, so that is the E step. This is all you'd need to implement in the E step. These three lines essentially. So fairly simple. You'd implement this one, and this one after each other. They're the three lines of code you need to implement on your computer. That's the E step. Now let's talk about the M step. And the M step's slightly more fiddly. So let's go back to our lower bound. Let me just write out what the lower bound is to remind us at the top of the page here. So you'll remember that the free energy as a function of Q of S and theta is equal to sum on S, Q of S, log P of X given S and theta plus sum of, sorry, I've missed a term off here, times P of S given theta. This is the log joint here, plus sum on S, Q of S, log Q of S. And actually this term in here has a minus sign in front of it. So this is something that we talked about in the last video, how you'd move between the lower bound and this alternative formulation of the lower bound. And for the M step, we said we're interested in optimizing this with respect to theta. And so we can ignore this term because there's no theta dependence in it. So all the action is in this first term here at the front. So let's go and calculate that for our mixture of Gaussians case. And we know for our mixture of Gaussians case, this thing is going to look like a Gaussian. And this second term is going to look like, it's going to be related to our prior probabilities, our pi k's. So we plug in those things. And this sum over here becomes a sum over all settings of our latent variables. And our latent variables can take one of k settings. So I can just sum over k to handle this sum out the front. So putting all that together here, we get the formula below. Let me just sort of go through in a little bit more detail how that lines up. So notice here, log p of x given s and theta, that's the log of a Gaussian. That's going to be these terms in here, the log of a Gaussian. And this term here, our prior, will be our log pi k's. That's this bit in here. Our q of s's, of course, are given by this part of the free energy. And then our sum over s is replaced by our sum over k here, because s can take one of k settings. And of course, here we've got n latent variables. So we need to sum out over all of those n latent variables out the front here. And then all of this junk here to do with entropies and things, that's what this constant term is going to soak up. And that's the thing which doesn't depend on the parameters. So hopefully it's kind of clear now how the free energy here can be calculated for our mixture of Gaussians example. And in particular, this first term that's required for the M step. Good, okay. And so in the M step, we need to optimize this with Q fixed. So this thing out here will not change, and all the terms inside the log will change. So we're going to optimize this with respect to the parameters. And the way we're going to do this is we're first going to optimize with respect to the cluster centers, or the means, the mu's. Then we're going to optimize with respect to the variances, and then finally we're going to optimize with respect to the pi's. Okay, so let's do the means first. So where is the dependence on the means? Well, the means just show up in this part down here, just this quadratic form in the middle. There is no other mu k's appearing in the free energy. So let's compute the partial derivative of the free energy with respect to the jth mean. So do df by d mu j. So when we do that, we'll just pick out the jth element of this sum. All the other parts of the sum will depend on other cluster means. And so their derivative with respect to mu j will be 0, and we just get the jth term. And then for that jth term, we just have to differentiate this quadratic form. And that will give us a factor of 2 coming down here that will cancel with this 2 here. And we'll end up also with a minus sign coming from the fact that there's a minus sign in the middle of the quadratic form here that will cancel with this minus sign here. And we end up with this expression. So the sum over n is retained, of course. We've got rid of the sum over k from the derivative, but this sum over n comes down here and is retained by in this form. Sorry, my pen's just stopping working for some reason here. And this contribution comes in here. And we set that equal to 0 because we're trying to find an optimum of this. And if you then rearrange the expressions that result, let's just fill in the steps here. So you'll get sum on n equals 1 to n q sn equal to j of xn over sigma j squared minus sum on n equals 1 to n. I'm just expanding out the multiplication here to make this absolutely explicit. Mu j over sigma j squared equals 0. So notice that we can just cancel out the sigma j squares because they multiply both contributions. And also notice that mu j does not depend on n. So I can take this mu j and I can pull it outside of this sum here and write this thing as minus mu j like this. And then that gives this expression. And then if I solve this thing for mu j, I take this thing under here and mu j to the right-hand side, it should be obvious, hopefully now, that we end up with this expression here. And what I want to do now is just spend a couple of minutes talking about this expression and trying to understand, you know, what's going on in this expression and exactly does it make sense. Okay, so let me just get rid of the stuff at the bottom so we can think about this for a particular example. And I want to first think about the following case. I want to think about a case where the cluster assignments in here, so the Q, S, N equaling to J's, these are really confident assignments. So in general, this thing, remember this is the thing that we also called our responsibilities from before. This is our RNJs that we talked about before, responsibilities. These things are numbers that we can put into a matrix, and the matrix has n equals 1 through to big N rows, and it has j equals 1 to big K columns. And each entry in here, so this might be, you know, R11, that tells us how likely data point 1 is coming from cluster 1. And, you know, this entry in here, which is RNK, is how likely data point big N comes from cluster big K. And the rows must all sum to 1 here. So in the case where our clustering is really confident, what we might get is things like this. We might get these things filled up with zeros and ones. Might look like this. So this corresponds to really confident assignments where we're dead sure which cluster each data point comes from. And in that case, you can see that this thing is starting to look like S from the k-means algorithm, SNK from k-means. It's a hard clustering again, and the R's are playing exactly the same role as the S's. So in general, the R's will allow soft assignments. We won't necessarily get hard assignments out, but if they did give hard assignments out, and that will happen when the clusters are widely separated from one another, in those cases, R and S correspond. And then if we go and look at the way the means are updated, you can hopefully see that in the case where the Q's are hard, where either they take the value 0 or 1, and these are equivalent, again, just to stress it, as the R and J's. In the case where we get hard assignments, this thing will again collapse back to the mean of all of the data points xn such that they are in cluster J. Okay, so we're going to get back exactly what we had before. On the bottom, when we sum over the data points here, just to make this explicit, that involves like summing over columns. So if this is the jth column, you would just sum down the jth column and count how many data points are assigned to the jth cluster. And the top here just sums up all of the x's for those data points that have been summed to that cluster. And then when you divide the two, you get the mean, like I've been saying. So in the case where you have hard assignments, the update for the cluster centers is exactly what you'd get from the k-means algorithm. It just says compute the mean of the data points. In general, though, the update allows the assignments to be soft. And in the case where the assignments are soft, the denominator here just says, what's the total probability mass assigned to the jth cluster, averaging over all of our data points. And the top says, take the weighted average of the xn's, where you weight by a soft number now, which is how plausible do you think it is that the data point came from the jth cluster. You get soft weights in the top rather than hard weights, and then you divide the two. Good. Okay, so hopefully this is fairly intuitive now what this update is doing. You can think of what the E-step has done in a way here as filling in the values of the hidden variables for us. So because we're operating with this log joint distribution here, what we're essentially doing is filling in the values of the hidden variables by averaging over the probability that we came from each one of the clusters. And then the M step then ends up actually looking very much like supervised learning. It's a bit like we know which cluster each data point comes from. So I think it's a generally useful perspective. And anytime you use the EM algorithm, you can think about as a bit like using the E step to fill in the values of the hidden variables in a soft way. And then the M step is a bit like just carrying out normal supervised learning, where in the supervised learning problem that we're talking about, it's like knowing the value of the underlying hidden variables. And if we knew the value of the hidden variables, then everything becomes easy. Okay, so that was the update for the cluster centers. Let's do the second parameter now. Let's do the sigmas, okay? So the variances of the clusters. Okay, so let's do the same thing again. When you take the derivative of the jth cluster variance, that just picks out the jth term in this sum. All the other terms in that sum do not depend on the variance of the jth component. And there are two places now where the variance turns up, in here and in here. This one, when we differentiate it, will give us something like 1/2 sigma j squared. That's going to give us this term in here. And the second place where it turns up, we have to differentiate this thing. And when we differentiate this thing, we'll get a minus sign cancelling out with this minus sign. So we get something that looks like plus xn minus mu j squared, just from the quadratic term here, which is unaffected. And then when we take the derivative of 1/sigma j squared, we'll get 1/sigma j to the fourth. And as I said, the minus that comes from that, the negative sign that comes from that, ends up cancelling this one out the front. So that then gives rise to this term here. And now we can rearrange in exactly the same way as I've talked about before, and we'll end up with the following update for the variances. And again, hopefully this, if you stare at it, makes sense. On the bottom, you've got exactly the same term like we had before, which is how much probability mass is assigned to the jth cluster and over all of our data points. And on the top, it says compute for each data point how far it is away from its mean, square it, and then weight that by how likely it is that we think it came from that cluster. This is the responsibility again. So it says compute sort of the average squared error to the cluster mean, sum that up over all data points, and then divide by the total mass, probability mass coming from that data point. And again, if this were a hard assignment and the responsibilities collapsed to ones and zeros, it would just say, for each cluster, go through all the points assigned to it, compute the squared error, and divide by the total number of points assigned to that cluster. So it's like computing the variance of that cluster around the cluster center given by the step above. So again, pretty intuitive, I think. This is sort of might be the update you attempted to come up with by hand if you wanted to fix or learn variances. Finally, we're going to learn the final parameter here, these pi k's. So let's talk through that. And this is going to require a little bit more subtlety, because the pi k's are constrained variables. They're not free to take any value. And in particular, one constraint that's placed upon them is that they should sum to 1. So if we sum the pi k's over k, this thing we know has to sum to 1. The sum of the prior probabilities must sum to 1. And so when we're carrying out the optimization, we need to make sure we get a solution pack that obeys these constraints. They also must be positive as well, and non-negative. They could be 0, so non-negative in general. So the way that we're going to do that is we're going to have to use Lagrange multipliers. And in particular, we're going to put in the constraint that these things must sum to 1. We won't put in the positivity constraint. We'll just check at the end to make sure that everything is hunky-dory with respect to the positivity constraint. So we'll double check that once we carry out this optimization and solve for it, that it is indeed true that the pi's are between 0 and 1. The constraint will make sure that they sum up to 1, of course. So we add in a Lagrange multiplier here. If you haven't seen this in too much detail before, I know it comes up a bit in the PCA stuff that you've covered. You should go and read some more about it. The Mathematics of Machine Learning textbook has a section on this, and Bishop has a really nice appendix on this, Chris Bishop's book. There are lots of other resources which cover this as well in a good way. So the way you use Lagrange multipliers is you add in a Lagrange multiplier which multiplies by the constraint, and the constraint is that the pi k's when summed over should sum to 1. So that gives us this term in here. And now we optimize the sum of the objective, f, and the constraint. So when we do that, we're going to get 2 terms. We'll get one term which comes from this log pi k thing. So that comes from our objective. So when we differentiate log pi k, we get 1 over pi k, of course, and then we get this term coming in and multiplying it, and that gives us this first term in here. And then when we take the derivative of the constraint bit, so the constraint bit in here, we take the derivative, there's a pi k that will turn up from taking this derivative here. We take the derivative of pi j with respect to pi j, that gives us 1, and so we just end up getting the Lagrange multiplier appearing in here. And now when you rearrange this and substitute back in the constraint that everything must sum to 1, you get this thing, okay? Which again, when we unpack it now, will look really, really intuitive. It says, for each cluster, sum over all the data points and figure out how much mass has been assigned to it when aggregating over all of the data points. This is exactly the numerator that appeared as a denominator that appeared in the equations above. So you sum over all the data points, say, with what total probability mass did we come from that cluster, and then you divide by n the number of data points in here. So if everything was hard again, if we had hard assignments again, this term here would just sum up the number of data points assigned to the jth cluster. So we might have 5, and then you divide by the total number of data points in the data set, which might be 100. And so the prior probability just ends up being 5 over 100. More generally, this allows, of course, for soft assignments again, like we talked about before. Okay, so again, I think you could have written down this update. It's sort of simple to see that these pi j's defined in this way lie between 0 and 1. So we also obey the positivity constraint, even though we didn't explicitly put that constraint into our optimization. Good. Okay, so if you were going to go and implement this on a computer now, you just have to implement the 3 equations on the right-hand side here. You'd update your cluster centers first, then your variances, and then your pi j's, where these things are just given by the E step, and in the E step we labeled these things R and J. So again, the M step in this case is going to take another 3 lines. So the E and the M step together take 6 lines between them. Great. Okay, so hopefully that has shown how, in a fairly intuitive way, we can derive the updates for the EM algorithm for a simple 1D mixture of Gaussians case. In the next video lecture, we are going to just walk through applying that EM algorithm to a couple of simple data sets and just look at its properties and then talk around, how does this compare with what we would get out of the k-means algorithm. Although the derivation here has looked at the 1D case, the examples we'll look at actually are 2D cases. And the only change you really have to make when you do that is here where we optimize for variances. In the general case, we'd want to optimize for covariance matrices. And that needs, a little bit more matrix algebra where you need to know how to differentiate with respect to a covariance matrix in here, which sounds perhaps a little bit scary, but actually turns out to be fairly simple. And there are rules you can follow to do this. Great. Okay, so next time we'll look at some 2D examples and run the algorithm on it.